right, in our last video, we figured out how to look at an atom and know how many protons, neutrons, and electrons were present in the atom. So for example, if we had chlorine with a mass of 35, then we would look up chlorine on the periodic table and see that chlorine's atomic number is 17, therefore it has 17 protons. If its mass is 35, then it would need 18 neutrons that they would add up to 35, and the number of electrons present in chlorine 35 would be 17, so that we have an equal number of protons and electrons so that our overall charge is neutral. Now, find chlorine on the periodic table and notice that its mass listed on the periodic table is 35.453. That's because that is the average mass of 1 mole of the element. And you'll remember that 1 mole is equal to 6.02 times 10 to the 23rd particles. So you have a whole bunch of chlorine atoms, and that's what we get as the average mass. So the mass that's on your periodic table is an average of all of the different forms of chlorine that show up. And if you have a mole, then that's 6.02 times 10 to the 23rd, and then it would be measured in grams instead of AMU. Before we talk about the different forms of chlorine that are present, which lead to it having an average atomic mass of 35.453, we just need to work a little bit on units. If we have a singular atom that is very, 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 very tiny, and the mass would be measured in AMU. So we go to the periodic table, we find potassium. That's in group 1, and it is 39.0983. So we'll go to the nearest tenth, so we'll say 39.1 AMU. If we have a mole of potassium, we would still have the same numerical value, but now it would be measured in grams because a mole is much more massive. We have a lot more atoms, 6.02 times 10 to the 23rd to be exact. So now the unit is grams. Works the same way if we have a compound. So if we have a compound, CO2, what we do is we look up carbon. We have 1 carbon, and carbon's mass to the nearest tenth is 12.0, and we only have 1 of them, so that gives us a mass of 12. Oxygen, we have 2 oxygens, so we have to count oxygen twice. To the nearest tenth, oxygen is 16.0, so the 2 oxygens together would be 32.0, so then we add those up, and we get 44.0. And again, we want to go to the nearest tenth when we do our masses, so both of these answers will be 44.0, but the thing that will differ is the unit. If we have a singular molecule that is incredibly tiny, so we would need to use AMU as our unit. Once we have a mole, that's an amount that we could actually see, measure on a scale, hold in our hands, so that's going to be 44.0 grams. All right, so now we have isotopes. This is a big vocab word for us, so we need to know what an isotope is. So an isotope is when we have the same element, therefore we will have the same atomic number, which would give us the same number of protons, but they have a different mass because the number of neutrons is different. So for example, down here, we are going to indicate the number of protons and neutrons and electrons in carbon 12 and carbon 14. So carbon 12 and carbon 14 are isotopes of each other because they are the same element, carbon, but they have different masses, 12 and 14. So what we're going to do now is we just have to look at the periodic table And we are going to write down how many protons, neutrons, and electrons are in carbon 12 and carbon 14. So we find carbon on the periodic table, and carbon will have 6 protons. If its mass is 12, then we would also have 6 neutrons. And since it does not have a charge, we also would have 6 electrons here. Now in carbon 14, the protons would still be equal to 6 because its atomic number is 6. The neutrons would be equal to 8 this time because the protons plus neutrons have to add up to the mass. And the electrons would still be 6 because there's no charge, so we have an equal number of protons and electrons. So we can see that they have the same protons, same electrons, but they do have a different number of neutrons, which then will give them a different mass. So this helps to explain how we get the mass that is listed on the periodic table. So the mass that's listed on the periodic table is the weighted average of the naturally occurring isotopes for that element. So if we look at carbon, carbon's mass on the periodic table is 12.011. So that accounts for the fact that carbon 12 is way more abundant than carbon 14. So that one counts more. So it's not a straight average, like where you add them up and divide by 2. It's a weighted average where you account for the percentage. So the formula to calculate the weighted average atomic mass, you will take the mass of the particular isotope times its corresponding percentage. And we know that when we multiply by a percent, like say 75%, we multiply by 0.75, so expressed as a decimal. And then we do that again with the next isotope. And then you wouldn't do that a third time if you had 3 isotopes and so on. So we'll do this example for nitrogen. So you do need to grab your calculators. So what we'll do here is we will take this exact mass times that percent as a decimal. So we will write that all out, 14.00374 times 0.9963. Now, normally I would write this all in one line, but I don't have a huge amount of space, so I'll have to write it below. We would do the same thing with the 15 number, so 0.00108 times, we still have to move the decimal on there, so 0.0037. Now, before we even pick up our calculators to get the two values that we'll add together, and then to eventually get our final answer, common sense should tell us that this one, the 14 one, is way more abundant. So my mass is going to be way closer to 14 than it is to 15. So it's kind of like in class, if you have scored an 85 on almost every single assignment that we've done, and then one assignment you weren't too hot and got a 50, that one singular low grade shouldn't be pulling you down too far. So most of them have mass of about 14, so our final average should come out to be pretty close to the 14 number. Okay, so now we just put this into our calculator. So we have to type this all in. And that would give us, for this first value, the 14 times the 0.9963, would give us 13.95 plus some additional digits, but we want 4 significant figures because of that. So we're good with 13.95. And then we do the 15 number, but again, we have to type in the whole thing, not just 15. So 15.000108 times 0.0037, and that gives us 0.056. We only want two significant figures for that one. Then we add them up together, 13.95 plus 0.056, and that gives us 14.01. So that would be the weighted average atomic mass for nitrogen. Notice it's much closer to that 14 number than to the 15. All right, so we're just going to do another example here. This time we have 3 isotopes of magnesium. Magnesium with a mass of about 24, 25, and 26. We notice that the about 24 one is most common. So we're going to be closest to 24, but it's going to be a little bit above 24 to account for the magnesium 25 and 26. This time we can just kind of do our work right in our chart. So we can just move the decimal over 2 spots. So that's going to be 0.7899, 0.100, and 0.1101. Then we'll multiply those 2 numbers together, and then we'll get our 3 values, and then total them up. So we put in the first one, 23.985043 times 0.7899. That gives us 18.95 if we round to 4 significant figures, because the percentage had the lower number of significant figures. All right, we do the same thing with our next set of numbers, 24.985837 times 0.1000, which gives us 2.499. We would want 4 significant figures for that one. And then our last one, we type in the whole number, 25.982593 times 0.1101, and that gives us 2.861. All right, then we add those 3 numbers up, 18.95 plus 2.499 plus 2.861, and that gives us a grand total of 24.31 for the weighted average atomic mass for magnesium. Our answer makes sense because it's between our 3 numbers, but closer to 24 since that is the most abundant one. And again, isotopes are same element, so magnesium in this case, but different masses because they have a different number of neutrons. And then the way that we get the mass that is listed on the periodic table is it's a weighted average of all of the different isotopes that occur naturally for that element. You do need to be able to do this calculation. It is one that always shows up on the Regents exam, and it is not listed on your reference table. So you do have to remember this calculation and be able to do it.